Yes, the call went through. Matt, I need help. I think I'm lost in the forest surrounding my house. How long do you think it'll take for me to get back home?
Well, that depends. Is it an infinitely large forest?
I don't think so.
Well, that's great. If that's the case, I've got the solution for you. Ergodic theory and recurrence, presented by Matthew and Ziki. So ergodic theory is a field of mathematics that studies the properties of dynamical systems over a long period of time using measure theory.
Here are some set notations illustrated by Venn diagrams that you'll see throughout our presentation. Sets are a group of numbers or items that will be referred to as capital letters. The circles represent each set, and the grayed area is a space of interest.
Measure theory is a mathematical way to assign a size to any set using real numbers. The Lebesgue measure, represented by lambda, is a method of approximating the size of a set in R by covering it with intervals. It is worth noting that the Lebesgue measure of an interval is simply its length. So for my set A, as seen in this example, its measure would be 2.5. The measure of this set is equal to the sum of the measure of the smaller sets it is composed of. This is thanks to a property of measures called countable additivity, which basically says that the measure of non-overlapping sets is equal to the sum of the measures of these sets. A measure space defines three conditions for a measure. The first defines the space in which the measure takes place and is simply any non-empty set. In Lebesgue measure, X is often the real numbers. The second is S, or the sigma algebra on X. This is the collection of sets that we are allowed to measure in X. Finally, mu is the measure itself. Mu is always a function that satisfies these two properties. First, that the measure of an empty set is equal to 0, and second, that it is countably additive. Just a quick note, Lebesgue measure, noted as lambda, is an example of a measure.
Now on to transformations. We'll refer to transformations as capital letter T, but note that it is not a set, but rather an operator. A transformation is a dynamical system where time is measured in numbers of iterations, or number of times that we apply the transformation to a certain set. For example, transforming x once is noted as t to the 1 of x, or even just t of x, and transforming x twice is t to the 2 of x, which equals to the transformation of the transformed x, which is t to t of x. When we write t big X, right arrow at big X, it indicates that the transformation takes points of big X back to points in X. An example of a simple transformation is t of x equals x plus 1 on the real number line. If x is 1, then t of x is 2, and t2 of x is 3, etc. When transforming a set, we apply the transformation to each point of the set. These are the two main transformations that we will be using to demonstrate the different properties that characterize transformations. First, the rotation transformation, and second, the Baker's transformation.
So before we explain the rotation transformation, we need to take a moment to explain a mathematical operation called modulo. Modulo is an operation that finds the remainder of a division. For example, 5 modulo 3 is equal to 2. We will focus on operations using modulo 1, which can be likened to keeping only the decimals. For example, 1.3 modulo 1 is equal to 0.3. Now, consider a circle of circumference 1. If I were to move along the circle by a number, so for example, if I were to move by half a unit, it would mean going around half the circle. This is how rotation can be done by adding numbers modulo 1 instead of angles, where a rotation of 1 is the same as a rotation of 360 degrees or 2 pi radians. The rotation transformation itself is simply x plus alpha modulo 1, where alpha is any constant in the real numbers. So for example, if alpha is equal to 3/4 and we focus on the position of a set A from 0 to 1/4, we see that after one rotation, the rotated set A ends up at 3/4 to 0 and so on. So there are two important properties that transformations can have that we'll see later are important for recurrence and ergodicity. The first is invertibility, which basically says that for any set A, the inverse of any iteration of the transformation is measurable. The second important property of transformation can have is measure preservation, which says that the measure of a set A does not change after any number of transformations. We see that rotation is invertible since we can simply add minus alpha to return to the previous iteration, which is measurable. Rotation is also an example of a measure-preserving transformation because it does not change the measure of a set after transforming it. In the example, you can see that the measure of my set A in red remains 1/4 even after the transformation.
Our second transformation is named the Baker's transformation after the way that dough is kneaded, as shown in the GIF. But instead of a 3D dough, we will only observe a 2D cross-section that is a 1x1 square in the first quadrant with a corner at the origin. This mathematical formula for the transformation basically just states what is illustrated lower by the images. It squishes both sets, then places set B on top of A. When working in 2 dimensions, the measure of a set is equal to its area. It is then easy to see that this transformation is measure preserving since the area remains the same 1x1 square it started off as. The transformation is also invertible since it can be undone by separating the square into the top half and lower half and just going backwards on the transformation. We have another illustration to show what happens after we apply the transformation a few more times, which creates more alternating layers of set A and set B. This interaction of the 2 sets is named mixing. For a transformation to be mixing sets A and B together, it must, after an infinite amount of iterations, have the end set A's intersect with the first set B's area correspond to the product of the initial area multiplied together. As you can see from the math at the bottom of the slide, each set had a measure of a half to begin with, which makes a fourth when multiplied together, corresponding to the area of the intersect between mixed A and the right half of the square, which is the initial set. Putting the measure of B onto the left side of the limit just simply shows that the initial area of A was a half, and the transformed A now occupies a half of the initial set B.
Here we have an example of mixing in real life. If my initial batter is composed of 3/4 cookie dough and 1/4 chocolate chips, after infinite mixing, we'd expect this proportion to hold true even for smaller portions of the batter. So if I look at my set B, which is the cookie dough in 1 scoop, the intersect of the mixed chocolate chips with the scoop of dough represents the chocolate chips inside the scoop. The ratio of the measure of these chocolate chips to the measure of B is equal to the measure of A, which is 1/4. So in other words, my cookie is composed of 1/4 chocolate chips.
Mixing happens to be one of the strongest properties of a system, but some systems can partially satisfy the conditions, and those are deemed weakly mixing. To be weakly mixing, a system needs to have both recurrence and ergodicity, 2 weaker properties that we will now explain. So recurrence. Looking at a measure-preserving transformation, T is recurrent if for any set A contained in X, almost every point of A returns to A after some number of transformations. When we say almost every, it just means that it's up to a set of measure 0. N, which is the number of transformations it takes to get back to the initial set, is named the return time. The image shows that the transformation can take X lots of places until it eventually reaches its starting point. The X plus 1 transformation is not recurrent, while the rotation is.
Now let's move on to a very useful theorem for recurrence, the Poincaré recurrence theorem. It states that on a finite measure space, every measure-preserving transformation is recurrent. An important point in this theorem is that the transformation must occur on a finite measure space, which means that the measure of x cannot be infinity. To picture why this is important, imagine throwing a ball in a closed room compared to throwing a ball outside. In one example, you can catch the ball because it will come back to you, and in the other, the ball will probably never make its way back to you again.
A strictly T-invariant set is simply a set that is equal to its previous iteration. For T to be ergodic, a T-invariant set, any T-invariant set that can be found in the system has to either have measure 0 or have equal measure to the measure space. An example of a non-ergodic transformation is a rotation with a rational alpha. For example, if we use alpha equals to a half, which is rational, and observe the T-invariant set A, that is the union of 0 to an eighth and a half to 5/8, that it is not ergodic because the measure of this set is a fourth, which is not equal to either 0 or 1. On the other hand, if we use an irrational alpha, the transformation is ergodic because the irrational rotation allows a point to travel every point on the circle, making it impossible to find a T-invariant set other than the measure space itself. Because this irrational rotation is both ergodic and recurrent by Poincaré, it is weakly mixing.
So this brings our presentation to an end. Our goal was to simply introduce you guys to a few key concepts in ergodic theory and measure-theoretic dynamics. Taziki, do you have an idea of how long it'd take you to get out of that forest now?
Wait, that's it? How much time does that mean?
Well, if we assume that you're recurrent, and then it takes some number n of iterations. So in other words, you'll eventually make it home.
Oh no!
Thank you for listening to our presentation.